A machine built to run a digital copy of the cosmos is no longer science fiction. It's underway, turning equations into a universe inside a computer. From colliding galaxies to the curves of space-time, these simulations let us watch history unfold faster than any telescope and probe ideas we can't test in the lab. In this video, we pull back the curtain on how this cosmic computer is constructed, what data and physics power it, and why watching the universe simulate itself is more than flashy tech. It's a new way to think about reality. You'll see how computation meets cosmology, what these digital universes can reveal about our own, and what this digital cosmos could mean for science, imagination, and the future of discovery. Foundations of a digital cosmos. Foundations of a digital cosmos rest on translating the laws that govern real physics into scalable algorithms that can march through billions of years of evolution. Space and time become computable grids or ensembles of particles. Gravity is encoded as either Newtonian attraction in an expanding background or, for certain problems, as Einsteinian spacetime dynamics approximated with relativistic corrections, and the surrounding matter is treated as dark matter particles and gas. Initial conditions, seed structure. These seeds come from a Gaussian random field defined by a power spectrum shaped by early physics and constrained by observations of the cosmic microwave background in large-scale structure. The result is a reproducible starting point for simulations. Discretization choices drive what the virtual universe can resolve, and they determine how gravity, hydrodynamics, and feedback interweave. In-body particles carry dark matter. Hydrodynamics can be solved with smooth particle methods or with adaptive mesh refinement, each approach trading off simplicity, resolution, and numerical diffusion. AMR uses nested grids that sharpen around dense regions. SPH models follow fluid elements that move with the flow, smoothing properties over a kernel, which helps conserve mass and energy but can blur shocks. Subgrid physics fills the gaps. Subgrid models prescribe how gas cools, forms stars, and how energetic feedback from supernovae and active galactic nuclei shapes galaxies. Calibration matters. Because simulations cannot resolve everything, researchers tune parameters to reproduce key observables such as stellar mass functions, gas fractions, and the distribution of halo properties, while keeping predictions robust across resolutions. They test that different codes arrive at similar large-scale results in controlled setups. Cross-code comparisons under projects like Agora help reveal sensitivities to numerical choices and model assumptions, guiding the community toward reliable baselines. Uncertainty quantification remains essential. Validation comes from comparing mock skies to real surveys, from the clustering of galaxies to the statistics of weak lensing signals. Digital universes become laboratories. They allow experiments that would be impossible in the real cosmos, such as turning knobs on dark matter properties or feedback efficiencies and watching how the large-scale web reorganizes. But limits exist. Resolution ceilings, incomplete physics, and observational biases impose caveats, pushing researchers toward convergence studies and transparent documentation. The foundations, though, are sturdy. Consistent physics, careful discretization, and rigorous testing create a platform where simulation and observation can converse with trust. Architecture of the cosmic simulator. Cosmological simulators rely on a hybrid multi-physics core that couples gravity, gas dynamics, and, where needed, radiative processes. The architecture is modular, separating physics modules from the execution and first/O layers, so solvers can be swapped without rewriting the entire codebase. Compute workloads are distributed through domain decomposition and space partitioning, ensuring scalable use of thousands of cores. Data structures favor hierarchical space subdivision, such as octrees or adaptive meshes, to track dense filaments and emptier voids. A dedicated orchestration layer handles time stepping, synchronization, and checkpointing. Gravity is treated with a combination of long-range and short-range solvers. The long-range force often uses particle mesh approaches to accumulate mass on a grid. Short-range forces are computed with tree methods or direct summation in high-density regions. This hybrid strategy, often called tree PM, balances accuracy with speed. Load balancing relies on space-filling curves like Hilbert or Morton orders to keep each compute node responsible for roughly equal work. Gadget and similar codes popularize this approach, while Ramses applies a grid-based strategy with adaptive refinement to preserve accuracy in dense areas. Spatial discretization uses adaptive methods to refine regions of interest. Adaptive mesh refinement concentrates resolution where density peaks develop. Alternatively, moving mesh approaches track fluid elements as they flow, reducing numerical diffusion. Codes may implement both AMR and moving mesh strategies within the same architecture. The result is a flexible resolution that follows the physics rather than the grid. Yinzio, Ramses, and Flash illustrate grid-based AMR, while a repo demonstrates the moving mesh philosophy, each bringing its own trade-offs to the simulation of shocks and turbulence. Hydrodynamics can be solved with grid-based schemes or particle-based methods. Grid-based codes use Godunov-type solvers to handle shocks and turbulence. SPH variants model fluids with particles and smoothing kernels. Moving mesh codes blend the two philosophies by letting mesh cells move with the flow. This diversity lets researchers tailor the solver to the problem. Ramses, Yinzio, and Flash emphasize grid-based hydrodynamics, while Gadget leans on particle-based methods, and a repo bridges the gap with a dynamic mesh approach. Radiative transfer exposure is included in more advanced setups. Approximate ray tracing or moment-based methods offer scalable illumination effects. Chemistry networks track cooling and molecular formation in simple, efficient ways. Some architectures integrate Ramses RT or Arepo RT-style modules to study reionization and feedback processes. The goal is to capture how light interacts with matter without prohibitive cost. Ramses RT and Arepo RT examples demonstrate how radiation feedback can be coupled to evolving density fields within a single framework. First/O is a critical bottleneck in large simulations. Snapshot data is typically stored in standardized formats and organized by time step. Checkpointing supports restart after failures and performance optimization. In-situ analysis and on-the-fly visualization reduce the need to write massive intermediate files. Metadata catalogs record solver versions, parameters, and random seeds for reproducibility. HDF5 is commonly used for scalable data storage, while binary snapshot formats are still found in legacy pipelines and some codes. Parallel execution uses MPI for distributed memory and OpenMP for shared memory. Some codes leverage accelerators like GPUs to accelerate gravity or hydrodynamics kernels. Communication schemes rely on fast interconnects to minimize latency during domain exchanges. In practice, testers tune load balancing and time stepping to maintain efficiency as resolution grows. GPUs, when available, can provide meaningful speedups for gravity solvers and hydrodynamics kernels, but portability remains a key design concern to keep simulations adaptable across architectures. Starting from a rough initial density field, the architecture distributes work, refines regions of interest, and advances the simulation with synchronized steps. Snapshots capture the state of dark matter, gas, and radiation fields. Researchers often perform in-situ analysis to extract halos, filaments, and statistics while the simulation runs. The architecture's modularity makes it possible to replace a hydro solver without reworking the rest of the pipeline. Initial conditions are generated by tools like Music or Engine IC, ensuring consistent seeds and spectra across runs for reproducibility. The result is a flexible, scalable blueprint that can accommodate a wide range of cosmological questions without rewriting core components. Physics in the simulated universe. Physics in a simulated cosmos relies on discretized space-time grids and a suite of governing equations that run on high-performance computers to model gravity, electromagnetism, fluid dynamics, and radiation transport across cosmic scales. The rules must stay numerically stable. In astrophysical contexts, Newtonian gravity is often augmented by relativistic corrections in strong fields, while magnetohydrodynamics captures the behavior of conducting plasmas threaded by magnetic fields. Adaptive mesh refinement focuses resources where complexity rises. Smooth particle hydrodynamics and grid-based methods complement each other by representing fluids through particles or cells, enabling accurate treatment of shocks, accretion, and turbulence. Quantum effects enter via lattice field theories or effective semi-classical approaches. On scales relevant to structure formation, many simulations treat matter as a classical or fluid-like medium and encode quantum corrections through subgrid models or stochastic forcing. Lattice quantum field theory methods push into QCD and beyond. Monte Carlo sampling, stochastic differential equations, and the truncated Wigner approximation offer ways to simulate quantum fluctuations without solving full many-body wave functions. Observer effects are modeled as decoherence channels that reduce superpositions to classical outcomes. In the cosmic microwave background or early universe scenarios, quantum fluctuations seed structure, and the simulation must translate those seeds into observable patterns through transfer functions. The geometry of spacetime evolves alongside matter. General relativity is encoded through Einstein's equations, often solved with 3+1 decompositions and formulations like BSSN or Z4C to manage constraint equations during evolution. Curvature guides light and matter. Numerical relativity handles strong field regimes such as black hole mergers, gravitational lensing, and the propagation of gravitational waves through expanding backgrounds. Causal structure and time slicing choices influence numerical stability. Simulations must respect gauge freedom and ensure that coordinate artifacts do not masquerade as physical signals, a problem mitigated by constraint damping and convergence testing. Validation against empirical data anchors credibility. Simulated outputs are compared to telescope surveys, gravitational wave catalogs, and large-scale structure statistics to tune subgrid physics and resolution choices. Resolution matters. Subgrid models for star formation, feedback, cooling, and chemical enrichment approximate processes unresolved at the grid or particle scale, balancing computational cost against physical realism. Convergence tests check that results stabilize when the grid refines. Error budgets quantify truncation errors, sampling noise, and potential biases, guiding decisions about time stepping, domain size, and data analysis pipelines. The end goal is predictive power with transparent uncertainty estimates, data, calibration, and scale management. In a digital cosmos, data flows through a structured pipeline from initial conditions to final outputs. These data streams carry metadata that records how and where each sample was produced. Common formats like HDF5 and NetCDF underpin many storage layers, while bespoke binary formats optimize first/O for gravity solvers. Provenance tracks parameter sets, seeds, code versions, and run environments so results can be reproduced. Calibration ties the simulation to reality by comparing synthetic observables with real surveys and telescope measurements. Bayesian calibration, emulation, and sensitivity analysis are standard tools. Emulators built with Gaussian processes or polynomial chaos surrogates reduce the cost of exploring parameter spaces, letting researchers test how changes in physics alter the output. Targets include the galaxy luminosity function, matter power spectrum, and halo statistics under realistic survey masks. Managing scale means designing for performance, resilience, and reproducibility across petascale workloads. Domain decomposition, MPI, and, increasingly, GPU-accelerated kernels distribute work efficiently. Adaptive mesh refinement focuses resources where gravity and hydrodynamics demand detail, while coarser grids cover emptier regions. In situ analytics, checkpointing, and hierarchical storage reduce first/O bottlenecks and prevent data loss during long runs. A robust data management plan catalogs files, records lineage, and enforces metadata standards. Validation involves cross-checks against analytic expectations and mock observations. Data throughput is monitored with dashboards that flag anomalies in read/write rates and numerical drift. Storage and retention policies decide what gets kept, archived, or compressed for later reanalysis. Implications for knowledge and reality. A digital cosmos encodes the laws of physics and initial conditions into a computable framework, and that framework yields predictions, retrodictions, and patterns that researchers can compare with real observations. Knowledge accumulates as simulations are tuned and tested against data, creating a dialogue between what the model lets us compute and what the universe reveals through telescopes, detectors, and surveys. When a simulated universe reproduces features like the large-scale distribution of galaxies or the statistics of cosmic structures, scientists gain a form of practical confidence about the underlying physics. If discrepancies arise, they signal either gaps in the modeling, missing physics, or new phenomena to explore. The machine reframes what counts as evidence by turning theoretical ideas into testable, repeatable experiments at cosmic scales. It is a powerful laboratory in which hypotheses can be exercised without waiting for new celestial events. Yet confidence rests on the fidelity of the model and the care with which uncertainties are managed. Different choices about subgrid physics, feedback processes, or initial condition ensembles can lead to similar observational predictions. In other words, several competing models can fit the same data, and choosing between them becomes a matter of auxiliary assumptions and predictive power beyond the data at hand. Reality, in this view, becomes something that can be probed through computational experiments as much as through direct observation. If a digital cosmos yields predictions that consistently match measurements across diverse phenomena, those predictions become useful knowledge about how the universe behaves. But the boundary between what we infer about reality and what we simulate grows nuanced. A result might be valid within the code and its physics assumptions, yet contingent on the specific computational framework used. This raises questions about ontological status. Are we learning about the universe or about a particular model's internal world? Practically, the implications are profound for science and method. Digital universes support the design of observational campaigns, helping decide which measurements would most distinguish competing theories. They enable rigorous testing of data analysis pipelines, reducing the risk that discoveries arise from processing artifacts. They also expose the limits of our inferences by highlighting how sensitive conclusions are to assumptions about physics, resolution, and numerical schemes. Researchers can build ensembles, perform sensitivity analyses, and quantify how uncertainty propagates from initial conditions to final predictions. In this way, the machine becomes not only a conscripted simulator, but a structured partner in shaping what counts as reliable knowledge about reality. Verification, uncertainty, and limitations. Verification ensures that the software implements the governing equations of physics correctly and that numerical methods are applied as intended. It relies on a battery of tests. Common practice includes unit tests on individual modules, code reviews, and runs against analytic solutions or well-characterized test problems such as linear waves and shock tube setups. These checks aim to catch bugs, discretization errors, and misinterpretations of algorithms. Uncertainty in simulations can be categorized as epistemic, reflecting incomplete knowledge about the model itself and its parameters, or as aleatoric, tied to inherent randomness in initial conditions and stochastic subgrid processes. In cosmological contexts, initial conditions come from observations with finite precision, and the mapping from those measurements to a full three-dimensional field contains model-driven gaps. Subgrid models for star formation and feedback introduce parameters that are tuned to reproduce observed trends. Exploring these uncertainties involves running ensembles with varied initial seeds, different subgrid choices, and perturbations in physical constants within plausible bounds. Data assimilation can anchor simulations to real observations, but it does not erase fundamental errors. Limitations arise from the finite resolution that prevents a faithful capture of microphysics, and from simplified physics that cannot fully resolve radiative transfer, magnetic fields, or plasma effects. Subgrid models fill the gap, but they are approximations. Discretization choices, time-stepping schemes, and operator splitting can introduce numerical diffusion, artificial anisotropy, or energy non-conservation in long runs. The problem scales dramatically as structure forms. Even with powerful hardware, simulations must trade dynamic range for tractability, so conclusions about rare events or extreme regimes carry extra caveats. Long-term predictions shift from precise forecasts to probabilistic landscapes. To manage verification, researchers run cross-code comparisons, ensure convergence under grid refinement, and document fully deterministic seeds so results can be reproduced. They test energy and momentum budgets and compare outputs to multiple analytic benchmarks where available. Uncertainty quantification relies on ensemble statistics, sensitivity analyses, and probabilistic calibration to propagate input errors through the model and produce credible prediction intervals. Validation against observations remains essential. even when the universe itself is the ultimate data set. Limitations are made explicit in reports with caveats about subgrid physics, resolution limits, and the range of parameter space explored, guiding users to avoid overinterpretation. Ultimately, the aim is a transparent, reproducible relationship between models, data, and the questions being asked. Today we explored the machine that simulates the universe and what it means to create a digital copy of the cosmos, how physical laws get encoded into scalable models, how initial conditions guide evolution, and how the limits of computation and resolution shape what we can learn. We considered the kinds of questions such a system can probe, from gravity and quantum effects to the emergence of structure across cosmic time, and what a successful simulation could reveal about the universe's behavior and fate. If you're watching from a lab, a classroom, or a living room, your curiosity is part of this shared quest. You bring ideas, challenges, and wonder that keep this conversation moving forward. If this sparked something in you, drop a like, subscribe, and tell me in the comments what cosmic feature you'd most like to see tested in a simulation. In the next videos, we'll pull back the curtain on the algorithms, the hardware realities, and the ethical questions around digital cosmology, and we'll hear from researchers about where the field might go next. Thanks for watching, and first we'll see you in the next episode.